The Great American Eclipse. On August 21st, the moon will cross between the Earth and the Sun, casting a 70-mile-wide shadow onto the planet's surface that will cut a path across the U.S. from the west coast to the east. Those directly in its path, the path of totality, will experience what's called a total solar eclipse, when the moon completely blocks the sun's light. A total solar eclipse provides scientists with a unique opportunity to observe certain features of the sun, in particular, the mysterious corona. Understanding these features is not simply a matter of sating scientific curiosity, though. It's critical for a technologically dependent society, whose Earth-based instruments and satellites are impacted daily by solar activity. Research funded by the National Science Foundation, NSF, including through the NSF-supported National Solar Observatory, NSO, and National Center for Atmospheric Research, NCAR, is helping illuminate the intimate relationship between us and our closest star. Pictured, the very faint, upper level of the sun's atmosphere, called the corona, becomes visible during a total solar eclipse, sunspot central. Sunspots, which appear as dark patches on the sun's surface, called the photosphere, denote intense magnetic activity. At 7,000 degrees Fahrenheit, these areas are cooler, and thus darker, than the surrounding surface area, which can reach temperatures of 10,000 degrees Fahrenheit. Sunspot activity waxes and wanes during an 11-year cycle. During the solar maximum, when sunspots are more numerous, the Earth's atmosphere is rocked by geomagnetic storms, which impact everything from communications networks to satellites. Interestingly, an NSF-funded study also found that the Earth is bombarded by high speeds of solar energy during even quiet phases, called the solar minimum, when sunspots are fewer or have disappeared, a model sunspot. Scientists at NCAR's High-Altitude Observatory used a supercomputer to create this 3D, high-resolution image of a sunspot's dark central region, called the umbra, and its outer region, called the penumbra. The ability to accurately model the complex structure and dynamics of sunspots helps researchers better understand when they will emerge and how they will evolve. Being able to anticipate sunspot activity using advanced computer models of the sunspot cycle may help scientists one day forecast future solar storms 24 hours or possibly 22 years, one solar cycle, in advance of a storm. Coronal sneezes. Another type of solar eruption distinct from a solar flare is a coronal mass ejection, CME. These violent eruptions, which often occur alongside flares, send magnetic fields and plasma hurtling through the solar system. CME material traveling over 1,000,000 miles per hour can reach Earth in as little as 18 hours or as much as a few days. When this wave of magnetic material washes over the Earth, it interacts with the planet's magnetic fields, causing a geomagnetic storm that can disrupt communications, GPS and the power grid. It can also expose orbiting astronauts to unsafe levels of radiation. Understanding the magnetic activity that drives these events is critical to minimizing the damage they can do on and above the Earth. NSF's annual K-NU-A Solar Telescope, or KIST, will look specifically at changes in the sun's corona associated with CMEs and solar flares when it comes online in 2020. Flare up. As the sun rotates, its magnetic fields contort and become taut. Eventually the fields snap, producing an eruption of energy and light called a solar flare. The light from a flare will reach the Earth in 8 minutes, the speed of light. The flare's electromagnetic energy also travels at high speeds and in all directions, buffeting the Earth with high-energy particles that can swell the planet's upper atmosphere, called the ionosphere. Because radio waves bounce off the ionosphere as they travel, solar flares impact everyday technologies. Airplane navigation systems, cell phone communications and credit card transactions all rely on the stable transmission of radio waves through the ionosphere, which is disrupted when particles from flares further ionize this part of the Earth's atmosphere. NSF-funded scientists are working to better understand the dynamics behind when and how flares form. A recent study detected the emergence of small-scale magnetic fields in the lower part of the sun's corona that may act as precursors to a flare. Knowing how these eruptive events develop could help us predict future flares with greater precision. The middle child. Between the photosphere and the corona, the Sun's chromosphere roils and churns. One of three main outer layers that make up the Sun's atmosphere, the chromosphere often appears red as superheated hydrogen emits light. When viewed during a total solar eclipse, the red rim of the chromosphere is just visible to the naked eye. This image, taken with the interferometric bidimensional spectrometer at the NSO's Richard B. Dunn Solar Telescope, reveals solar features seen best through a spectrograph. These include bright areas surrounding sunspots, called plasias, that are associated with strong magnetic fields. A solar flare can also be seen erupting to the right of the sunspot in the lower right. Cool, thread-like features magnetically suspended above the sun's surface, called filaments or solar prominences, are visible in the center and upper left, hyperspeed. Many scientists are taking advantage of the upcoming eclipse to conduct one-of-a-kind research. Scientists at the NCAR and the Smithsonian Astrophysical Observatory are collaborating on an experiment that will take place aboard the NSF/NCAR Gulfstream V high-performance instrumented airborne platform for environmental research, GV-HYPER, aircraft. As they fly along a section of the eclipse path, their infrared measurements of the lower solar corona may lead to a better understanding of solar winds and space weather. NSF-funded researchers at George Mason University are combining citizen science and basic research to study radio wave propagation as the moon blocks the sun, which will cause a sudden change in the Earth's ionosphere. Their project, called Eclipse Mob, will analyze data from 200 custom-built radio receivers at schools around the country. A team at Boston University is looking to construct a high-resolution picture of the Earth's ionosphere using GPS signals from smartphones, which can measure the number of ions between the phone and a GPS satellite, magnetic mapping. This visualization by scientists from NCAR in Boulder, Colorado, shows a tangle of magnetic fields above the solar surface resulting from a coronal mass ejection, CME. The solar storms that result from CMEs create a turbulent front that can penetrate deep inside the Earth's magnetosphere. When particles from CMEs crash into the planet's atmosphere, they cast off their excess energy, which causes the Earth's atmosphere to glow and produce one of the world's most spectacular natural light shows, as seen in the next image, auroral storms. The aurora australis lights up the dark sky above the South Pole. Auroras, both the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere, appear when charged particles from the sun, carried by a solar wind, run headlong into the Earth's own magnetically charged atmosphere. More than just a dazzling light show, auroras are of interest to scientists because of their association with solar storms. The NSF-supported Aurorasaurus project leverages the power of citizen science by amassing data from thousands of aurora watchers around the world to help track the auroras in real time. Studying the data, scientists are hoping to learn more about the storms that can disrupt or destroy the Earth's communications networks and affect the planet's navigation, pipeline, electrical and transportation systems, polar opposites. This image reveals the magnetic field in the Sun's corona, derived from data provided through the NSO's Global Oscillation Network Group, or GOM. Magnetic field lines that are closed on the Sun are shown in blue, while those that are open are shown in red and green. The Sun, like the Earth, has two poles, similar to a bar magnet. On the Sun, magnetic fields wrap themselves up over approximately a 5 to 6 year period. They then spend the next 5 years winding down, relaxing and producing solar flares and coronal mass ejections to release excess energy. Scientists are not able to observe magnetic fields directly, so they use hot gases in the Sun's atmosphere to trace out magnetic field lines. During solar maximum, when sunspots are numerous and solar activity is at its peak, magnetic lines surround the Sun. During solar minimum, which is when the upcoming eclipse will occur, there is more magnetic activity at the Sun's equator and poles. Given the corona is not expected to change much before the eclipse, Scientists at the NSO used current observations to create a coronal magnetic model that shows where they expect to see field lines concentrated during the eclipse. Most powerful solar observatory atop Haleakala on Maui, Hawaii. Construction of NSF's KIST, the world's soon-to-be largest solar telescope, nears completion. The telescope's state-of-the-art instrumentation, including a 4-meter primary mirror polished to a surface roughness of 2 nanometers, 2 billionths of a meter, will give scientists an unprecedented view of the Sun, and help answer long-standing fundamental questions in solar physics. Fundamental research conducted at KIST will also have real-world impacts. For example, scientists using the telescope's coronagraph to create an artificial eclipse that blocks out the Sun will seek to better understand the fundamental physics behind solar eruptive events. This, in turn, will lead to better models of solar activity and improve the ability to forecast space weather. Citizen science. Perhaps one of the greatest impacts of the upcoming solar eclipse is the excitement it has created among people of all ages. For the first time in history, modern technology and social media make it possible for millions of people viewing the eclipse to contribute to scientific research. Images and data they collect and share through CitizenGate, Continental America Telescopic Eclipse, and other citizen science projects will be analyzed for years to come. NSF's support of fundamental solar research and the development of sophisticated instruments to investigate our star's mysterious nature will continue to advance the understanding of the Sun and its impact on our planet. The images in this National Science Foundation gallery are copyrighted and may be used only for personal, educational and non-profit, non-commercial purposes. Credits must be provided.